All right, we have 40 minutes left. And with that time, I would like to give you an introduction to genetic algorithms, which I think are really cool. And I would have liked to spend more time on this. In fact, I was hoping we'd have time to even write our own genetic algorithm, but we're not going to have time to do that today. So I'm just going to talk through this, and maybe we can set up another time to meet when we actually work through writing a genetic algorithm. But I'm just going to explain basically the basic concept of what a genetic algorithm is. Let me get my bearings here. All right. Okay, so let's just list some. So this is genetic algorithms. And so some of the drawbacks, I guess, to put genetic algorithms in perspective, some of the cons of gradient-based algorithms are that they are not good for the following problems. So I'm going to say not good for. So they struggle in the following situations. So so we've already talked about having multiple local minima or saddle points. Etc. So, places where the gradient goes to zero can wreak havoc on these if we're trying to find a global minimum. They're also not good for non-continuous design spaces. And that can be in our objective function and or constraints. So even if your constraints are non-continuous, that design space, if those fences are non-continuous, that can wreak havoc on the on gradient base. I'm going to put this, large numbers of design variables. And I'm not really convinced that it's really the number of design variables that's the problem. I think the challenge with the larger number of design variables is that you have a larger dimensional space. And as you get into these larger dimensional problems, there tend to be more local minima that you can fall into. So I guess, this is what I've seen as a con, the larger number of design variables. But I really think that this just goes back to the fact that when you have large, a very high dimensional space, that you tend to have more probability of having more local minima. And so I really think that that's the real problem here. The number of design variables is not necessarily the issue. Okay, and then finally, one that we haven't mentioned, but is a real challenge with these, is that they are not good for discrete valued functions. Okay, so what do we mean by discrete valued functions? Sorry, not functions, design variables. Design variables. Okay, so what if our design variables, one of the things going into our system is the number of something, the number of slices or the number of wings that you have on an airplane or the number of tires you're going to carry on a car. Well, you can't have 4.5 tires, that it's not a number that you can use to compute a gradient. You can't add a little bit more, 4.1 tires and 3.9 tires. You have to stick with discrete numbers. You can either have 4 tires or 5 tires or 3 tires, but you can't have a real number, any number between those. And so there are a lot of optimization problems out there that require some kind of input of a discrete number of things, and you actually want to optimize on the number of things that you want. So for example, in DBF or design build fly, sometimes what they have you do is carry a certain number of packages or balls or something from point A to point B. And so you write this big optimization algorithm. Well, how big does my airplane need to be? Well, it depends on how many things you're carrying, right? Well, you can't carry 4.5 of those things. You either carry 4 or you carry 5. And so an optimization algorithm has a hard time. A gradient-based optimization algorithm is not very useful for trying to come up with the number of packages you want to carry. So, one way to use gradient-based is to treat it as a real variable. And if it comes up with 4.9 packages, that is the optimum number of packages you want to carry, then you just round that up to 5, right? You round that to the nearest integer. But again, your design space may be very sensitive to that variable, and maybe it would have been better to have 4 instead of 5, even though if it were a real number, it comes out with 4.9. So there's, anyway, discrete valued design variables is a challenge, and gradient-based optimization really is not good for that. So this is one motivation to use genetic algorithms, or it really, here's 4 motivations, 4 reasons that you might consider using a genetic algorithm over a gradient-based optimization algorithm. Okay, so I'm just gonna write down some terms here that we will be talking about. I'm not gonna define each of these right now. I'm just gonna write them down so you're watching for them. So there's something called a chromosome or a gene. There's a fitness, generation, selection, crossover, and mutation. So these are some terms that we'll be discussing here in in this genetic algorithm. So let's pretend like we have some design space here, and I'm just gonna kind of draw a box over here. So we've got some design space, and we really don't know what that looks like, but we assume that there might be many local minima in there, and so what we'd like to do is try to find the global minimum, and so how are we going to do this? Well, again, you can go back to, there's brute force methods. We could call every single combination of our design variables, and I don't want to rule that out. Sometimes that's actually really useful because it gives you insight into the design space, and sometimes just calling all the different combinations can be faster than actually optimizing, especially if you have a really tight design space and there's only so many combinations to look at. But for larger design spaces, for larger dimensions, then that really becomes infeasible really quickly. And so we've got to come up with a better algorithm to do this. So genetic algorithms are based off of biology, basically. It's based off of this process of natural selection, that the history of the world has been going through for a very long time, where good things that are really good at something survive, and things that are not very good die off, right? And the things that survive generally are the things that then populate and create the next generation of things, and the next generation hopefully is a little bit better at that whatever we're measuring, and so we can have generations that get better and better at something. So this is just the process of natural selection, that obviously nature has been going through for a very long time. Okay, so in order to do this, the first thing we have to do is come up with what's called a gene. Okay, so a gene is simply, or a chromosome is simply a definition of our solution, or one point in this design space. Okay, and so we usually, let's say, I guess just for the sake of argument here, we're going to use X and Y as our values here along each of these axes. And so a simple way to create a gene would be just to say, we're going to call this gene, and we usually write them vertically simply because that's how your DNA or genes are written, you know, in the scientific community. But anyway, so we have we're going to have a split here in this gene where we have the top portion of this gene is the X value, and the bottom portion of this gene is a Y value. Now, really in Python or any programming language, we can just see this as an array, right? We've just written it in a vertical form. The top part is the X value, or the first component in that array is the X value. The second component is the Y value. Okay, so this is one way to create a gene. Now, there's a lot of different ways to actually create a gene, even if we have two variables, X and Y. And technically, genetic algorithms like to decompose X and Y into a different kind of a gene. They call it a binary gene, okay? And so technically, that X value can be represented as an X or as a binary number. It's a series of ones and zeros, right? And so, so technically, this gene could be rewritten as a series of ones and zeros, you know, all the way down here, and we might have 32 or 64 or 128 different components of that gene that are just ones and zeros. But you can decode the first half of these into the X value and decode the second half of those into the Y value. Okay, so this is, you know, technically when people talk about genetic algorithms, this is the, I guess I would say, the preferred way of creating a gene. But there's nothing to say that the methods that we're going to go through here wouldn't work for the simpler approach where you just have an array. And I'll even talk about an example later where that array makes more sense than the gene of ones and zeros. But in any case, this idea of a gene, all we're doing is coding up, you know, this is how we're going to represent some point in this design space. It's represented by a gene that can then be decoded, or the information can be pulled out to tell us exactly where we are in the design space, okay, in this n-dimensional design space. Okay, so that's the definition of a gene. Next, we need to understand, well, what's the fitness of this gene? And I've seen this also defined different ways, if I remember right. I hope I'm not leading you astray on this, but basically you can think of fitness as like your objective function. And so we're going to test this gene to see how fit it is for a specific scenario. So we might plug in X and Y, and this is equivalent or similar to having just a function where X and Y comes in and out comes the objective value, right? But we're going to call that the fitness. How fit is this gene for what we're trying to do? And we want that fitness to decrease with time. All optimization algorithms are trying to minimize, right? So we want that fitness to decrease as the solution gets better, right? As we get closer to what we're looking for. So again, so fitness, I guess I'm just going to write fitness is something analogous to a function. And basically what it's going to take in is this gene, and out it's going to spit a single value that tells us the fitness of that particular point in space or that particular gene, okay? Okay, one other thing here I guess I forgot to mention is that we're also going to have a population. So we initialize this with we initialize this genetic algorithm by randomly, at least I guess most genetic algorithms are initialized by choosing a population size. So let's choose, you know, maybe 20 or something, maybe I have 20 dots on there. And I'm just going to randomly seed this by picking random combinations of X and Y and creating 20 genes. You know, my first population size is 20 here. I'm going to create 20 genes of these randomly chosen locations here. So for our example here, we're going to say we've got a population of 20. And so we have 20 genes that we've created that represent 20 randomly chosen locations within this design space, okay? And usually populations are more on the order of 100 or 1,000. I'm just doing it according to what I've kind of drawn here, okay? Okay, so then after we have a population of these genes, the next step here is that we're going to go into a selection process. And there are a number of ways you can do selection. What I've coded up in the past is what's called tournament selection. So tournament selection. And basically what we do is we run each of these 20 genes through the fitness function, and we see how fit they are. And we award we select the top number of those. We can choose 5 or 10, or 2, we can choose as many of those as we want as the winners of that tournament. So we send this population through this test, and for purposes here, we're going to select 10 winners, okay? And those 10 winners, we're going to call the parents of the next generation, okay? So I'm gonna rank these and take the top 10, and we're going to call those the parents of the next generation. And those parents now are the genes that are going to be used to create our next population. Okay, so we have 10 parents here, and so there's a number of ways that we can now we do two things here. We're going to do crossover and mutation in order to create the next generation or the next population here. And so crossover, let's draw our 10 parents here just as vertical lines. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so each of these genes has the same length, same number of characters inside of it. Those can be zeros and ones, or it could be just an array of values. And so we're going to do genetic algorithms do one or both of these two things, of crossover and mutation, to create the next generation. So basically what we're going to do is we're going to select genes A and B here, and we're going to choose a crossover point. And that can be, for our purposes here, maybe we want to choose halfway down, because the top represents X, the bottom represents Y roughly. And so we're gonna cross these over, and we're gonna create, there's a number of combinations that we can create here, but basically we can take the top portion of A and combine it with the bottom portion of B, for example, right? And that would be a new gene. So from these two, we're gonna get a new gene here that has the top portion from A and the bottom portion from B. Let me move my, okay, so that's a new gene that was created from parents A and B. And A can be mated, so to speak, with any other of the 9 genes here, right? So we got C, D, E, F, G. And so we can come up with many combinations that would create a new generation. In fact, we can come up with easily another population of 20, but like I said, usually we're working with populations on the order of 100 or 1,000. And so that process of crossover, there's a lot of different ways to do that, and you can kind of dream up almost how you want to do that. Now, there are some sophisticated ways to do that as well, for choosing what this point right here is called the crossover point. And you can move that up and down on your gene. Maybe you want to, we have maybe 20 or 30 characters inside of this gene that define this gene. And so, we can cross that over at any point. We can cross over just the first part. We can cross over halfway through. We can cross over 3/4 of the way down. So you can choose a crossover point, and then you're basically just going to swap that with whatever gene you're crossing it over with, right? So, and that creates a new child that was based off of those two parents, okay? Okay, so after crossover happens, so we're gonna call this crossover, then this gene can go through something called mutation. And mutation can take on a few different forms as well. So in mutation, let's just write that original gene. Let's say that the original gene was 1010, Well, basically, in the process of mutation, we have some probability that any one of these characters could flip signs or flip values or be mutated by a certain amount. So since we're working in a binary sense here, we would basically go down and say, there's maybe 5% probability that any one of these characters would change. And so we run some random mutation algorithm on those and say, hey, for this particular gene, we're going to the random number generator came out that we're going to flip that first flip that first one. Since it's binary, it can only be 0 or 1, and the rest are the same. Okay, so again, there's many different ways to handle mutation, but at the end of the day, all we're doing is saying that we are slightly adjusting this gene away from what it what its parents naturally crossed over to create. Okay. Now, I've shown an example here in binary, but let's say that we have a series of number here, and we have 3.3 and 2.8 and 5.1 and 6.0, and that's our gene, right? Well, then in this mutation process, you can say that there's some probability, some 5 or 10% probability that any of these values are going to mutate, and you can give it we can say we're going to mutate the whichever number is randomly chosen by a certain percentage, 1%, 2%, 10%. Again, there's many different ways to do this, but maybe the mutated gene now basically looks the same, 3.3, 2.8, but it has a 5.3 here and a 6.0. So this is an example of mutation using real numbers. This is an example of mutation using a binary representation. Okay, you can see that from what we've done here, you can now easily create a whole new generation of, all of this stuff comes across to create a new generation of genes. Okay, and so now let's say that we created 20 or 100 of these, and now we go back into the tournament selection, and we have these all compete, and we're going to now reserve the best from this generation to create the following generation. Now, one alteration to this method is that you can allow the parents of the previous generation, the 10 best from the previous generation, to compete with the new generation. And that's where this is a little bit different than biology. Of course, in biology, that old generation usually dies off and they don't exist anymore, and you're left just with the new generation. But in genetic algorithms here in the computer-based world, we can keep these guys around, and now we have the new generation of 20 genes, and we can add in these previous 10 parents and let them compete as well, because maybe some of these parents are still the best gene that we have in the entire pool, and we wouldn't want to get rid of those, right? We would want to keep them as a parent for the generation after that. So anyway, that's one variation, I guess, in genetic algorithms, is that you can allow this parent generation to hang around and still compete with future generations until they naturally die off from genes that beat them out in that tournament selection. Okay, so we just simply repeat this process now. We add generations, we go through a crossover, we go through tournament selection, choose new parents, we cross them over, we mutate them, create a new generation, and we just keep going through that process until we decide that we've done enough generations, or there's a number of ways actually to determine this. So I'm just going to say repeat until and how are we going to decide when we want to end? Well, you can set a specific number of generations. That's one way to do it. You can set you can, within each generation, you can look at you can look at some statistical information. So you can look at the average fitness of each generation, the maximum fitness, the minimum fitness, the standard deviation of that fitness. And so you can look at some statistical information. Oops, that's an L. Of the generation, or of just the top 10, or of the parents, right? You can look at some statistical information about the parents, and eventually you're going to see that this kind of converges. So what we would, let's say that we are looking at the best fitness overall as a function of generation. So down here we have generation, and so 1, 2, 3, 4, 5, and we're going to have a bunch of generations. And at first, the best fitness that we had was there. And we're going to see that usually in the first few generations, it drops off rapidly, and then it starts to kind of level out. And then once in a while, we'll have another solution that will drop down a little bit. I probably should have drawn this a little differently. So we drop down rapidly, maybe we level off for a little bit, and then we drop down again, level off. But eventually you kind of flatten out on, you can keep adding generations, but your best group, or the statistical average of these, or the absolute best solution really isn't changing much, even with future generations. And so basically at some point you just have to choose that you're done and you stop running this. There's really no way to prove that that you have found the best case, that you're at a global optimum. There's really no way to prove that you have found it. Like in gradient-based optimization, you can take a gradient, that you're at the bottom of that puddle or whatever, or of that valley, and that every direction is uphill from you. But there's no way to prove that in genetic algorithms. However, genetic algorithms do have a much higher probability of finding the global minimum, because of how it has searched a larger portion of the design space. If you come back over to these examples here, this design space, all the points on here are all the points that these optimization, these gradient-based optimization algorithms were even testing or running, right? Where, or maybe I should come back here to be more technically correct. This includes even the line searches and things, right? So these are the only points that the gradient-based optimization algorithm even knows about in the design space. It's never looked outside of these points, where in a genetic algorithm, you naturally search a much larger region, and children are a combination of the previous parents. And so you just naturally get more spread across the region, and have a higher probability of getting to a global minimum. Okay, so that's the basic method that is, the outline of a genetic algorithm. Let me just explain one time. So I wrote a genetic algorithm years ago to solve a specific problem, and I thought I'd just explain that real quick. So if you guys have ever played the game where you write a note to somebody, but you swap out all of the letters in the alphabet with different letters, so you have to have like a key. So I'm just going to write up here. We have a key. Sorry about my handwriting. I'm getting a little sloppy, so I'm trying to write fast. But let's say that we have the whole alphabet here, A, B, C, D, all the way down to Z. And you pass your friend a key that says, whenever I put in A, I really mean X. And whenever I put in B, I really mean L, and C is N, and D is G, and so forth, right? So you have to have the key in order to decipher what this message is, right? Otherwise, it just looks like a bunch of gibberish. Well, my friend and I decided we were going to write a genetic algorithm to solve this problem. And so basically, you would just pass in, you would pass in a paragraph, or a sentence or something, right? So what would actually get passed into this is a series of words, and the algorithm didn't have access to the key. What its job was to solve for the key that solved this problem, right? It was to find the key. If you only had the message from your friend and didn't have the key, is there a way that you could solve that? And so basically what we would do is create genes then that were 26 characters in the alphabet. So there's, 26 things in here, and in each location was a different letter. And so as these genes crossed and mutated, they would, swap with other genes. But then after we did that swap, we had to rework the gene because you couldn't have any repeats. You couldn't have A show up in two locations along here. So when you swapped with other genes, you had to kind of clean up the gene to make sure that it was still a standalone gene that only had one instance of every letter in the alphabet. So there were some extra steps like this, and there often are in genetic algorithms. So you have to kind of clean up your genes or do different methods of mutation or crossover just based off of what the problem is that you're trying to solve. But anyway, we were able to and then on the tournament selection, the way that it did that was all it did was, so it would use its key. So each of these genes was a key, and it would basically plug in that key to the message, and then that message, each of the words in the message were checked against a dictionary. So we had some big file that was just a dictionary, and it would try to look up each of those words and see if it existed. And if it existed, then it would get a point for that word existing, or a minus or something for the word not existing in the dictionary. And so as it got closer to the solution, it would get more and more points for having more and more words that were real words out of the dictionary. And so anyway, this actually worked really quite well. And we found, of course, that it was easier to solve the longer the message was, because it had more information, more things to test in the dictionary, and could get points more easily when it got, like the letter A, for example, shows up a whole lot in these messages because it's just right. So as soon as it could get that, then or the and the short letters, and the more words there were, the more easily it could find the solution. And actually, sometimes we would write a message, we would find that there was more than one solution. It would come up with an answer to what that message was that didn't make any sense, but it was all perfect English in the sense that every word actually existed in the dictionary. So there's more than one solution sometimes. So anyway, that's just an example of when I've used a genetic algorithm, how we set up our gene, and for each of your problems, you want to think about how to structure this gene in order to make it worthwhile or useful for the specific problem that you're looking at. Okay, before I take questions, I just want to I'm going to drop this in chat. Here's a link. To kind of a cool thing online that you can play with the genetic algorithm. So this is just a post. This guy named Jason Brownlee. He does a lot with machine learning. But anyway, he's got this whole post about how to write your own genetic algorithm. And so he kind of walks you through the process. Here's a genetic algorithm from scratch, and he's using Python here, so that's really nice. Anyway, so you can just, if you want to write your own, you can go through his tutorial. Basically, here's an example. You see children. So there's different terms for these things. Your children come from those parents, obviously. And I'm guessing that this is the population, POP. Anyway, he has a specific problem that he applies it to. You can see his genes here. They're just arrays, so that's pretty straightforward. And so here's the gene, and his is a binary gene. And then here's the value that it's returning. So this is our, the best value that it was able to find up to that point. So anyway, he's got an example here for a continuous function. And you can, anyway, and then here's his output for his genes and the values. So anyway, lot of cool things you can do with genetic algorithms. There's a lot of different ways to approach it, a lot of different ways to write your code, a lot of different ways to define the problem or to define your gene. And but anyway, they're very powerful algorithms, and you know, based off of biology, which we're all human and we've all been through this process, or at least our ancestors have all been through this process to create who we are today. And anyway, it's just kind of this really cool approach to optimization that I think has a lot of merit and possibly still a lot of room to grow, you know, as we learn more things about how biology really works and how to make better decisions about how to do crossover and mutation. Like I said, there's a lot of different ways to do that. And those are areas where there's probably still room for even better methods to be developed. So, okay, questions?
Is the difference between the fitness function and the selection tournament function? Just the difference is the fitness function will give each gene a rank, and then the selection function will compare those ranks with other genes.
Exactly.
Okay.
Yep. So your fitness is like this function, and then the selection, basically all you're doing is after you've run all of your 20 or 100 or 1,000, you know, whatever you've got in that generation, you run them all through the fitness, and then you rank those, and that's called selection.
Yeah, so the selection is when you compare
ranks
between genes, and then the good ranking ones get move on, and the others don't move on.
Exactly. Yep.
Okay.
Yeah, so there's a lot of knobs you can turn on these, obviously. You know, how big of a population do you want? You know, how big is each generation going to be? How many are you going to preserve as parents for the next generation? How are you going to do the crossover? How are you going to do the mutation? There's a whole lot of knobs here to turn that are less, I would say, mathematically based, although there is some mathematics behind the crossover mutation methods that are out there for probability and you know, some of them, for example, at the very beginning of the process will allow very large mutations, and then the mutation will taper off with time as you should be progressing towards an optimum. Then the mutations are more constrained, right? So anyway, so there's different things like that are done, but it's much less theoretically based in the terms of like calculus, you know, that we've been using for gradient-based optimization, where you can make decisions based off of, you know, information that you have from a mathematical sense a little bit better. So
yeah.
Can I make a comment, Dr. Hunsaker?
Yes.
Thank
So we
you,
did
Dr. Hunsaker, for hosting this. I just need to hop off really quick. Sorry, Corey.
Yeah, you're fine.
You're good.
Thanks for coming, Kyler.
I just wanted to mention in my parallel programming class, we did a genetic optimization algorithm. And rather than doing a tournament, what we did is a lottery system. So you rank all of your population based on fitness, and the ones with high fitness, you give a lot of lottery tickets to. And the ones with very low fitness, you give like 1 or 2 lottery tickets to. And then you draw, you know, X number of lottery tickets for the next generation. So it gives some of those bad ones a chance to move on because maybe they have good genes.
Yep.
Anyway, it's a way to keep from getting too good too quickly and ending up in the local minimum. But that's just another way to do it.
Yeah, that's you're exactly right. Yeah, so there, like I said, there's lots of different ways to do the selection. And you're exactly right. What I've pointed out here really favors, you know, lucky people in that first generation that happen to be close to a good solution, right? But like you said, it preserves the good ones, and maybe too rapidly, right? Maybe there are other points out here where they were just off a little bit, but it cost them a lot, and we want to keep their genes around. So different ways of keeping diversity in the population is really important in genetic algorithms. And so that's, you know, that's partly what we're doing with this mutation down here, is trying to keep diversity in there. But another way is through how we handle the tournament selection. So yeah, excellent point. Thanks.
So just a question with that. So the lottery system would work well if we had a function similar to like the rastrogen function on that Wikipedia page, that first one that had a bunch of like just bubbles everywhere.
Yep. Mm-hmm.
That's where a lottery would be good, because
It could be. I mean, lottery, any of these could be good. It really just, it depends. See, the challenge with a lot of it depends on where that first generation randomly ends up. You know, whether or not the lottery is going to help, or preserving the top ones. You know. But that's true of every generation. You know, it just depends on where that generation ends up, if which one of those you want to use. So there's no, I wouldn't say there's no like perfect algorithm or perfect settings. You really have to play with whatever your function is and play with all the knobs you can in these genetic algorithms to see which one is going to converge to the most probable solution, you know, and most quickly, because obviously you want to get there as quickly as you can, but you also want to make sure that you've reached a good solution. So I guess I'm not prepared to say that lottery is better than the tournament selection for a specific design space. It just depends on too many other things. So, but lottery is good in keeping your generations a little bit more spread out as you go through generation. You know, keeping more people out in the fringes here, just in case there's another optimum out there that we need to find.
Okay. Okay. Yeah.
Okay. Well, that basically wraps it up. I hope that this has been useful to you guys. Yeah, I'd be real interested in feedback, you know, what you wish that you would have learned that we didn't cover. I think we covered most of everything that you wanted to talk about. If I come back here to our original, we talked about multiprocessing. Hopefully you have a foundation, benefits of various methods, basic understanding, how to debug. I hope we've covered that to a certain extent. Hopefully what we've gone through gave you exposure and experience and tips for convergence. Yeah, anyway, I just hope that this was time well spent. And like I said, if you have any feedback or suggestions for what I could do in the future to change this, if I do another workshop like this, you know, I'm all ears.